Hi, everybody, and welcome to week 2, assignment 2. And today we are joined by Alex Yun, and he's going to be taking us through the regression model assignment. So let's start by finding out, Alex. Welcome. Who are you? How did you end up taking this program or delivering this program?
Hello, everyone. My name is Alex. I'm one of your TAs. I am kind of in this space already, so intersection between health and AI. And yeah, I'm looking forward to taking everyone to this journey.
What did you study? Where did you study it? How did you end up in AI?
Sure. Okay. So I originally got my bachelor's of science in psychology and human biology at the University of Toronto. I did affective neuroscience research, and I was originally interested in emotion. And I kind of really enjoyed learning about computational tools to study those topics. So I decided to sort of make a shift and pursue my degree in computer science for my master's degree at the University of Waterloo. And from there, I studied artificial intelligence, machine learning, and affective computing. And now I'm working as a data engineer at a health AI startup.
Fantastic. All right. So Alex, you can get your model up. Just a quick reminder, my name is Shingai. I'm the course director for this program, and we're here to teach artificial intelligence in healthcare. Thank you so much for joining us. We're going to walk through this coding component of the assignment, and we'll talk about it. We'll run the code. We'll see what the outputs are. And then after that, we'll talk about the actual assignment questions that we need you to complete at the end of the session. All right, so Alex, could you make that a little bit bigger? Your font is a bit small.
Yep. Does that work?
Yeah, that'll do. Okay, that's good. That's good. All right, over to you, Alex. Take us through what we're doing here.
Okay, great. So this is our case study, and we're going to go through the regression models. So essentially, we have a data set that includes some basic demographic and health information on patients. And importantly, what we care about the medical cost. So we can sort of question two topics. That's one is regression and one's classification. So as you know, for a regression task, we have some sort of continuous variable, in this case, the medical cost. So our goal is to predict medical costs using a linear regression model. And for classification, we deal with discrete variables. So things like yes or no, in our case, whether the beneficiary is a smoker or a non-smoker. So we're going to predict one's smoking status using a logistic regression model. So going through the actual cells. So here, I'm just importing various packages that's relevant to our model as well as just data analysis. So first, we're going to import the data set. And see what's in the data set. So here's a sample of the data set itself. So we have things like age, sex, BMI, number of children, one's smoking status, region, as well as charges. So this is called a pandas data frame, which sort of holds this data as a data structure. So moving directly into the data analysis portion, this is a pretty standard practice. So we're going to check the dimensionality of the data frame. So how many rows and columns are there in the data set? And then we move on to the descriptive statistics. So things like centrality, so mean of the data itself, and the spread. So we can see things like minimum value, maximum value, as well as sort of the range in between. And it's important to look at the data type as well. So data type is sort of referring to things like, is it a numeric value? Is it a string? So is it characters, things like that. So I've sort of made a summary of each variable, their definition. So age is pretty self-explanatory, sex as well, BMI. Children, in this case, is the number of children covered by the insurance. Smoker region is the residential area of where the patient lives in the United States. And charges is sort of the medical cost, that the sort of the variable that we're interested in. And just going back, luckily we're not missing any data points. And this is really important to check, because if you're missing any data, it's gonna cause a lot of problems when you're doing the analysis as well as actually creating the model. So this is good news. And then there seems to be a duplicated row, which we'll just get rid of.
So Alex, from everything you've said, right, if I just recap it, we started off with the data set that's got all this health information. It came in the CSV format. That's the comma separated value, you can open it in a text file or in Excel. But anyway, you pull that into the Colab environment, and we're programming in Python. Mm-hmm. And then we've just started looking at it. So descriptive statistics, we've come across those, mean, median, mode, all of that kind of stuff. And already you can start to see, like when you start to see the ranges, for example, that can give you the maxes and mins, et cetera. It starts to give you a sense of who's in this data set, right? The different people that are involved. And then you looked at the different data types, and that matters because when we're doing regression, we're using numerical data, right? We're not going to be able to, there are ways we could massage data to pull that into regression, but for the most part, we're interested in that because we would need to have numerical data, right?
Exactly.
Right. Okay, great.
And I'll probably get into that a little bit down the line.
Fantastic. All right. And then once we've got the data, the other thing that you've provided is it's kind of like a smaller version of a data dictionary, but this is a very common thing when you're doing a data analysis is if you've gotten a data set from somewhere, you don't necessarily know what's in it. So Alex, thank you. You've done the heavy lifting of defining each of the variables for us. And then at this point, we're actually just starting to do some data cleanup. Now, normally this is probably the biggest part of projects, would you say, Alex? It takes.
Yeah, so I mentioned this later on, but really when it comes to sort of data science, machine learning, building the model and making the prediction is sort of the smallest part. So exploring the data itself, trying to get a sense of what is this data like? Are there any outliers? And you mentioned massaging the data a little bit and trying to visualize to get some sort of insight or to be able to make predictive guesses. So that would be the biggest portion.
Fantastic. All right. So we've just taken out the duplicate line and you're going to take us through some visualizations. All right, go ahead.
Sure. So, right. The descriptive statistics, of course, is giving you, the overall idea how the data is spread out. But, I personally am a very visual person. So it always helps to create these charts and graphs. In this case, we're sort of just visualizing the distribution of the medical cost. So you have the charges on the x-axis and then just the count on the y-axis. So if you can tell right now, we have a pretty skewed distribution. This can be problematic especially when we're doing things like regression, because there are certain assumptions of normality. So here we can just do a transformation. In our case, we're using a Box-Cox transformation. And what that's going to do is just sort of smooth out the distribution and make it normally distributed. So voila, we have a much better looking distribution. And this will help with the actual model as well down the line. And then another sort of important assumption of linear regression is that we want to ensure that the different variables are not too correlated with each other, because then it's hard to sort of describe the results, and you're prone to sort of underfitting or overfitting depending on the situation. So we do that by sort of looking at the heat map, which is sort of just going to visualize how correlated each variable is to one another. So just from looking at it, this is sort of an arbitrary call, but the values are quite low, like 0.1, 0.04, and so and so. And you can also tell it's sort of gives you a nice gradient. So the higher you go, the more correlated the variables are to one another. So I would say just from looking at the heat map, I would say the variables are quite independent. So we can move on. And these are just additional graphs that's going to help us sort of get insights about the data itself. So in this case, we're looking at age, BMI, as well as the number of children. So number of children, of course, it's a numeric value, but you're not going to be able to have 1.5 child. So sort of treating as like a categorical variable or discrete variable here. Yeah, so BMI, for example, it's really nicely distributed. And then essentially we can make several judgment calls or make hypotheses based on this. So using prior knowledge, chances are the older you get, the more money you'll be spending on healthcare. And that might be true with BMI as well, right? The more obese you are, the more likely that you're going to have ailments and stuff, and so you end up spending more money. So, and in addition, BMI, of course, you get this nice numeric values, but I think we tend to talk about it in terms of different categories. So whether that's underweight, normal weight, overweight, and obese. So we can sort of create a new feature or a new column where we take these numeric values and put them into different categories. So when I do that, so for example, this patient with a BMI of 27.9 is categorized as overweight. So taking this, we can visualize that again. And this time, we're sort of looking at the relationship between these relevant variables with the medical charges. So as we suspected, as one gets older, the medical cost is likely to go up. And looking at the BMI categories as well, people who are either overweight or obese, you can see that their medical cost is higher than those that are underweight or normal weight. And number of children, in this case, it's hard to make that judgment, but again, it's nice to visualize this information. Okay, so we're going to move on and look at rest of the variables. In this case, we're looking at sex, smoker, and region. So these are just number of females versus males in the data set, as well as smoker versus non-smoker. Clearly, there are a lot more non-smokers than smokers. I do note that sometimes this imbalance of the data set can be problematic when you're doing data analysis, because then what that does is when you create a model based on this data, you're learning more from the samples that have non-smokers, which means that it can, our model might be more biased and more sensitive to non-smokers. In our case, this is not a huge problem, but it's something to keep in mind. And then the regional differences in the US, they're fairly well spread out. And then again, we're going to do the same thing where we're going to look at the relationship between these variables and the medical cost. And interestingly enough, that men tend to spend more money on healthcare, and not surprisingly, smokers, the medical cost is going to be higher. There seems to be a regional difference, especially those that live in the southeastern part of the US. They tend to spend more on healthcare. Of course, these things can be affected by lifestyle choices and differences in climate and what have you. There are many factors. Of course, these are interesting questions that you can address with more relevant data. Okay. And so I'm going to go over additional plots where we aggregate some of the features to capture a little bit more nuance within the data set itself. So here we have two box plots. So we're going to look at, again, the relationship between one's smoking status and the medical cost. But on the left, we can also see the differences, the sex differences. So in general, so even within those who smoke, male are sort of incurring more medical costs than females. And in the case of non-smokers, there seems to be very little difference. On the right hand, we're sort of doing the same visualization, but we're looking at different BMI categories. So in this case, those that are smokers, but especially those that are overweight, are sort of way off and driving up the medical cost in the data set. So again, we've done sort of a bunch of visualizations looking at different variables, but it's important to keep in mind that sometimes aggregating some of the variables together can bring more insights, basically. Okay. Any questions or clarification?
Yeah, so when you started, this was exploratory. You were looking at the data set. There was, you didn't have an objective. You looked at the data set and you thought, well, what could be interesting that came out of it? And now you've actually got some concrete insights just by doing the data analysis. When we talk about the actual assignment, we're going to talk about, how reliable are insights from an analysis like this, and to how far can you take them, right? Just based on a few slides and a few charts. Just the one comment is, in terms of the regression model, there are two main things that we need to do. We need to establish the target variable, right? The thing that we're trying to understand, the thing that we're trying to reduce uncertainty about. And then we need to establish what of the variables we're going to try and use to reduce that uncertainty. Which of those explainer variables are going to help us, understand the target variable better? Can you talk a little bit about how you came about that? Is this after the analysis of the data that you said, okay, maybe this would be a good target variable?
Sure. So I think whenever you sort of ask a scientific question, it's hard. You're not going to be 100% unbiased, right? So you already have some sort of narrative that you're thinking of. So in my case, when I saw this data set, what immediately jumped to my mind was the medical cost, right? What will I be able to predict, is there a pattern in terms of medical costs? Will I be able to predict how much one spends on healthcare given their demographic information, right? So this is a sort of a pre-generated question. And of course, the other case is sometimes while doing the exploratory analysis, you might be able to come up with new questions, right? And that's sort of what ended up happening with the classification problem, specifically looking at one's smoking status. So just visualizing, especially these two aggregate bar plots, it was box plots. It was very clear that, okay, there's clearly something going on with some of the variables in relation to whether one smokes or not.
Got it. Okay, so what's the next phase of the analysis? So you've got your visualizations. What do we do next?
Right. So so far we've dealt with supervised learning, right? Which means that we already have sort of the correct output labels, and we're trying to predict some sort of outcome. But especially when you're sort of just in the exploratory phase, we can also utilize clustering. Of course, clustering is sort of fall under unsupervised learning, where you don't exactly have the outcome in mind. And this is really just sort of diving in and let's see what happens, right? Let the data sort of tell us what's happening. So in this case, again, it was kind of obvious that BMI has sort of a huge influence on medical charges at this point. So those are sort of the main interests. And we're going to use k-means clustering. And k-means is just an example of a clustering algorithm. It's a very popular algorithm. And here, what this visualization is just showing is you do have to sort of determine what the optimal number of clusters might be. And this is, of course, you can sort of arbitrarily pick, but using this visualizer, we can actually determine that 3 clusters is optimal for our data set. And using that to initialize, this is the result. So these are different data points, and the X is sort of showing the central portion of each cluster. So again, 3 clusters, and we can kind of see that there are different groups that's being observed. So now you have an option of sort of going more in depth to sort of pick out, okay, what's actually happening? What are the factors that might be causing these clusters? And we might call those like latent variables, hidden variables that might not be observed, right? We originally had 7 columns and these features and what have you, but there could be variables that were not specified, right? And often what clustering does is to help you find those latent variables. But for the purpose of this assignment, we're sort of gonna move on. But just to show you, we could have come up with similar conclusion just by aggregating additional variables, right? So before we are aggregating the smoking with sex and then smoking with BMI status. Now we're looking at BMI. Here I'm grouping them into the different categories, right? And you can clearly tell that these separate into nice clusters. And then on the right, I think this one's also interesting. It's looking at the BMI, and then you can clearly tell the difference between smoking and non-smoking. And this is actually quite similar to the cluster that we observe here.
So if the way to think about clustering maybe is that, so if you took the data points and you just spat them onto the grid, And then if they were the same color, you wouldn't really be able to tell what was happening, right? They looked like they were all over the place. But then once you apply the k-means, then you can actually now start to separate them. And so there are different ways to do clustering, but if you think about the location on the grid and the algorithm looking for, well, which data points are near that location, that's maybe a simplified way to think about how these groupings are taking place. And then from a visualization perspective, you've added colors to it. So immediately it's clear that, oh, that's one cluster and this is another cluster. So that works really well.
So just to add to that, yeah, the sort of this manual aggregate plot, I'm manually adding in the colors so we can visually see the distinction. Whereas in the k-means algorithm is sort of doing that for us. So it's going to find those boundaries for us and then determine these are the different cluster centroid, and these are the data points that belong to that center.
Got it. Okay, what's next?
Right. Oh, I think that's just an additional plot. Okay, so right, we've sort of finished the exploratory data analysis as well as clustering. So it's fair to say we have a pretty good grasp of what's happening with the data set. And then before we get to the actual modeling and prediction, we have to pre-process the data. And this is sort of where the massaging the data might happen. So in our case, just to bring it back, when we're dealing with regression model, we want to make sure that we're working with numeric values, right? Specifically with regression models, if you remember, we have things like sex, which is male, female, in this case, and then smoker as well. There's smoker, non-smoker, and region. We're divided into 4 separate regions. But essentially, we're going to code this into a numeric value. So what that means is sex now will be transferred to 0 and 1. So that's female, male accordingly. And then smoker, that's going to be 0, 1 as well. And the regions will be 0, 1, 2, 3. So, right. So you can tell that sex here, female is now 0. Smoker, yes, that's going to be a 1. And then the region southwest is going to be 3. And of course, the charges we've transformed earlier so that we could make it more Gaussian, normally distributed. Okay, so moving on to the modeling portion. Again, doing the linear regression first. Here, we're so we have the original data set, and we've done the pre-processing where we've manually or artificially encoded some of the variables so that it would fit our model better. And then now we're going to only keep the features that are relevant. So, so we're going to drop basically the original values that's not encoded. Right, so we end up with age, BMI, children, sex encoded, smoker encoded, and region encoded. So these are the variables or the feature that we're going to use to predict the medical charges, right? So we're separating the ones that we're going to use to predict and the outcome variable that we're going to predict. And this sort of method here, train, test, split. This is a common practice in machine learning and data science, where when you're training, we're basically separating a portion of the data that's only meant for training. And then when we actually sort of assess or evaluate the performance of the model, we're going to use data that was not part of the training. This is so that we can be sort of more objective and minimize bias in our model. So here, again, we're using a linear regression model. And after specifying the model, we're going to fit our data into that. And this is sort of the actual coefficients of the model, so to speak. So if you remember, y equals mx plus b, right? We have a bias term here and the different coefficients. Okay, so our model's done. And of course, the model's useless if you're not going to do anything about it. So we make predictions using the test data set that we set aside. So we have a bunch of equations that we're going to go through, but getting the results first. Okay. So I have both mean squared error as well as mean absolute error. But I can sort of describe them simultaneously. So really what they're representing is just the difference between the actual values and the predicted values. So how accurate is our model, right? So obviously we want to be as close to the actual value, right? The prediction that we make should be as close to the actual value. So, right, and in our case, we have 0.35, 0.39. So these are pretty close because we want to get to 0, as close to 0 as possible. And R squared is called the coefficient of determination. And it's sort of, as you remember, we create a model and we fit our data into the model. And it's sort of determining, okay, how well did we fit these values into our model? And the value actually ranges from 0 to 1. And in this case, we want to be as close to 1 as possible. And our model is showing 0.82. So that's performing quite well.
So if we had to visualize what's happening here is you still have that Cartesian plane, you still have you're plotting basically one thing against another, and you're trying to predict one of those things. So you've got all those, say, the usual, the dots on the chart, and then you draw a line of best fit. And that line of best fit is the model. That's the line, right? And so when you're trying to reduce the error, you're just trying to measure the distance between every actual data point and the distance between that data point and the line, because the line is the model. So the way that you've said it, you're saying the line is what we're predicting is going to happen, the line of best fit, which is the model. And we want to compare actual values versus the line. So for the regression model to work, for the whole concept of regression to work, we have to obviously minimize that error, the distance between each data point and that line of best fit. And then overall, the way you measure the success of your model or how well it was able to do that is with the R squared. And you've expressed it here as a decimal, but it can also be a percentage. So you're saying 82%. And is that a good number?
Yes, again, these things, it's a little bit arbitrary, and it's a personal call. And of course, depending on the situation, you might want a higher number, or there's a little bit of tolerance. And yeah, 82, 83% is quite reasonable.
Yeah, I've worked in retail and we worked with numbers way worse than that. And then obviously, if you're in healthcare, you obviously want numbers way better than that, because the consequences and risks associated with using a model like this are significantly higher if you're in a healthcare context.
Mm-hmm. And that is something that we're going to get into during the discussion. Yeah. Fantastic.
All right. So we've just done the linear regression model, right? So that's the one with the line of best fit, like you said, y equals mx plus c. So that's done. We've now got the logistic regression. What's the difference between the logistic regression and the linear regression?
Sure. So I think the easiest way to think about this, and in our case, we're doing sort of a binary classification. So yes or no. right? Are you a smoker or a non-smoker? So in a linear regression, you're basically, again, putting that line of best fit, which, is going to be pretty linear, right? Hence the linear regression. And logistic regression, we're going to put a function in which it will sort of artificially transform that linear into what we call a sigmoid function, like sort of like an S, right? So all the values that fall under the sort of the bottom curve might be one class, and all the other class that fall into the upper curve might be the other class.
Got it.
And hence the binary classification.
Okay, great. And so it applies to anything that's a yes or a no, a 0 or a 1, a true or false, anything.
Right.
Binary. Okay, great.
Exactly. So in terms of medical testing, are you positive, negative, so and so? Yeah. Okay. So we're essentially doing the exact same thing as linear regression here. Again, we're separating the data set accordingly, and we're defining, in this case, logistic regression, and we're fitting our data into that model as well. Yep. And then make the prediction. And of course, in terms of evaluating logistic regression, we're going to have different metrics, right? Before, with linear regression, we're using mean squared error as well as R squared values. Now, we're going to use things like precision, recall, and F1 score that I'm going to get into. So let's look at this first. So also with classification, it's really helpful to sort of visualize using a confusion matrix, which is going to sort of show you these values. So given the actual true class, and we make predictions, so what we expected, and we can sort of separate them into true positive, false positives, false negatives, as well as true negatives. And obviously our goal is to sort of minimize false positives and false negatives. Okay. So right, so you can tell that our model's predicting very well. So, and looking at the precision recall values, and these values ranges from 0 to 1. And for non-smoker, precision is 1, or you could call it 100%. Recall is 95%. For smokers, 85%. Recall, 100%. And F1 score is sort of, you're trying to balance the precision and recall, which is depending on what your goal is, right? Sometimes you want higher precision than recall and vice versa. And F1 score is sort of trying to balance both.
Yeah, but you kind of want to watch that, right? Because you never want to be in a situation where you are accurately predicting one thing, but you are failing to predict,
Exactly.
Something else.
Yeah.
Got it. Okay, great. So that's the confusion matrix. And we've got some of those scores, precision recall F1. We've also got R squared, but we're really just dipping a toe in regression. Regression is a huge topic. You get entire textbooks on this, right? There's p-values and all sorts of other things when you do the full regression output. After we've done this, do you think we are in a position to really give some concrete recommendations based on an analysis like this?
I would say so. I mean, I think the model is quite robust enough, and it's performing quite well. I personally wouldn't have any opposition if someone sort of presents this data and they're sort of recommending some sort of a solution. But of course, that really depends on one's, let's say, risk aversion, right? Because there's always that sense of uncertainty.
Got it. All right.
And
Well,
you're absolutely right. So we're really just dipping into this, right? You can kind of view regression as we're just establishing relationships between different variables, right? Once you observe those different variables, you might engage in additional hypotheses testing where you're trying to sort of reject null hypothesis, right? That's where the p-values come in. That's where you might consider things like sample sizes, effect size, and all that stuff.
Yeah, there's a lot going on, and there's other types of regression as well that we won't get into today. So this is the model, the regression model, and we've got the clustering in there as well that Alex put together. Thank you so much, Alex. Really appreciate all your hard work putting this together. And the basis of the assignment is really us starting to work with these results to try and make a decision. So we're going to pause this the video here, and then look out for the next video, which looks at the evaluative questions and the critical thinking part of this assignment.